I realise this video might be a little contentious, and there's going to be some people who really don't get it. Be good to see some healthy discussion, but I suspect I'm going to get some hate. The trouble is, I've got this undeniable urge to correct the internet. So buckle up, let's get this done. Ta-da! If I had £1 for every time I've heard someone say sensor size changes depth of field, I'd be quite rich. The trouble is, simply not true. And hold on to your chair, because focal length doesn't directly change depth of field either. When people say aperture affects depth of field, or subject distance affects depth of field, or even circle of confusion affects depth of field, they're not technically wrong. It's just confusing because they're all simply describing effects. And they're effects we can all observe, but they are effects that only indirectly change the apparent depth of field. They don't explain what's going on. People will passionately argue that it's sensor size or focal length that changes depth of field, even when you can physically demonstrate that it's just not true. So I'm starting to think we've all been doing this wrong. By the end of this video, I'm hoping to be able to describe, in as simple terms as I can, one single measurable factor which actually defines depth of field. And as a bonus, I also hope that being able to visualize exactly what's happening might help us all understand depth of field as we shoot. But first, in order to make things simple, we need to cut away some of the clutter, remove from the discussion a couple of terms and definitions which clearly aren't working as they should. Let's start with circle of confusion. I'm setting up a shot with 3 objects. The middle one is set at the precise focal distance, which in this case is exactly 1 meter away from the camera. Remember, we don't measure to the lens, we measure to where the focal plane is, or the sensor inside the camera, usually marked with that little symbol. I've also got a rear pattern and a foreground object, both of which are placed just inside the limits of where I think my depth of field should be. I do that using my favourite photo app, PhotoPills. I'm using my A7 IV with a 35mm lens at f5.6 and focused exactly 1 meter away. We can see from the app that this should give me a depth of field that extends 12 centimeters in front of the focal point and 15 centimeters behind, a total of 27 centimeters. I'll place my foreground and my background objects just inside this distance to make sure. I'll take the shot and, that's not right. If we zoom in here, we can see that the foreground, it's not in focus. Why doesn't this work? There's nothing wrong with the app. PhotoPills is great. It's just that, like all depth of field calculators, it's using circle of confusion for its calculations. It has to. The problem is with circle of confusion. Imagine the light from a subject, in this case a light bulb, going through a lens, the iris, and hitting the sensor at exactly the right point to be perfectly in focus. You can think of this light as a cone shape, and when it's perfectly sharp, you end up with a singular circular point of light on the sensor. If the light wasn't focused on the sensor, that circle would get bigger. At first, because of the pixel density of your sensor, you might not notice. Everything would still be acceptably sharp. But as this blur spot gets bigger, there comes a point when you can see it's out of focus. At that point, the size of the blur spot is effectively the circle of confusion. On my Sony A7 IV sensor, that's 0.03 of 1mm, which according to manufacturer's figures is pretty much the same as every 4K full-frame digital camera around at the moment. Now I realise we need this figure for our depth of field calculators, and it's used in lots of optical theory. But as we've already seen, it doesn't work that well in real life. Circle of confusion was defined way back when everybody was shooting on film and they were printing the images on pieces of paper. Those photos were then observed by somebody with average eyesight at arm's length just to see if it was in focus. Now obviously this was all a little vague, so some standards needed to be set. It should be 35mm film printed on an 8 by 10 piece of paper and held 25 centimeters away from somebody whose eyes could resolve 5 line pairs per millimetre, and that does sound more precise. It worked well for years. The problem today is that on one camera we can shoot multiple resolutions in different aspect ratios, and we're using an infinite number of display devices all at different sizes, resolutions and viewing distances. And we're cropping, enlarging, zooming in post to get that perfect frame. At best, circular confusion figures are only useful as a rough guide to what we might expect from the calculations. And as we've seen, I'm just not sure how relevant they are to visualizing how we control depth of field. Obviously, that cone of light is a gross oversimplification, and we were only thinking about a single point of light. In real life, lenses are made up of multiple elements that bend the light to zoom and focus. In fact, the image reaches the sensor upside down, and the light is flipped through the point of convergence where all the rays cross. The focal length of the lens is the distance between this theoretical point of convergence, or more accurately, the optical centre and the sensor. But let's ignore all of that because we're trying to keep it as simple as we can. The final term I think we should simplify is aperture, or iris size, or diaphragm, or f-stop, or entrance pupil. When I think of an aperture of, say, f4, I tend to visualise that as a physical hole, 1/4 the size of the focal length of a lens. So a 50mm lens at f4 will have an iris size of 12.5mm diameter. But when we're thinking about brightness or depth of field, the important thing is how big that hole appears, but when we look at it through the front element of a lens. That's called the size of the entrance pupil, and it'll usually look a little different to 12.5mm. It's also quite difficult to measure. I tend to swap these terms around without thinking, but the principle's the same. So when I talk about changing aperture, I'm thinking about changing the size of the entrance pupil. Now I know that's not strictly accurate, but bear with me, I'm trying to keep things simple. So let's get to the whole point of this video. Remember that cone of light focused on the sensor when we were thinking about circle of confusion? Imagine that cone of light this time outside the lens, starting at a single point on a perfectly focused subject, and expanding as the light enters through the lens, through the diameter of the entrance pupil. It's all imaginary because in real life everything happens inside the lens, but bear with me. The important thing about this cone of light is this angle at the pointy end. This angle is the sole thing that determines your depth of field. If the angle is small, then it takes a long distance before the diameter of that cone gets large enough for you to notice that the light isn't in focus. If the angle is larger, then it's a relatively short distance before you can see the image is soft. On any given sensor, that angle is directly proportional to your depth of field. Nothing else matters. And there's only two ways you can change that angle. Firstly, you can change the size of the entrance pupil. The bigger the diameter, the fatter the cone, and the quicker things go out of focus. Or secondly, you can change the subject distance. Lengthen the distance between the entrance pupil and the subject, and the cone gets longer. Our angle reduces, and we have more depth of field. So to summarise, a long, thin cone equals a large depth of field, and a short, wide cone equals a shallow depth of field. Nothing affects depth of field more than the angle of this cone. I find being able to easily visualise that cone of light and its angle to the subject really helps my understanding of depth of field and how best to control it. But is there any practical advantage or maths we can use to help us determine the real depth of field from knowing that angle? Probably not. If you know your subject distance and your aperture size, then the angle is easy to work out. And once you know that angle, you can exactly match the depth of field for any aperture and any subject distance. For instance, if I have a shot with a 50mm lens, 1 metre away at f4, I know the angle is 0.7162 degrees. It's then easy to work out that at 2 meters away, I'd need to be at f2 to get exactly the same depth of field. Obviously at 2 meters away, you'd also have a wider field of view. If I also wanted to match the field of view and the depth of field, I can use that angle of my cone to work out that I'd need to have a 100mm lens at f4. All of this is very basic maths, especially in this example because we're doubling both the subject distance and the focal length, but the principles are always the same. Actually, this example is interesting because you'd think with exactly the same angle of view and depth of field, we'd have exactly the same shot. But obviously, because we're now on a longer focal length, we're changing the perspective between the foreground and the background subjects. Some people call it compressing the picture, and what we're actually doing is magnifying the background, making it bigger in the frame. I think it's this magnification of the background that makes a lot of people think you've reduced the depth of field by using a longer focal length. But it's simply not true. You've just made the existing depth of field look bigger in frame. You've enlarged the out of focusedness, but you've not changed it. Do a test at 2 different focal lengths with the same depth of field and crop the backgrounds to match the sizes, and you'll see there's no difference to how out of focus they are. All of this is interesting in theory, but if all you want is a rough guide to how much depth of field you can probably expect in reality, the traditional calculators and apps using maths and circle of confusion are probably still the easiest solution on set, even if you find you end up not being totally accurate. So why have I bothered to make this video? Well, I think it really does help our understanding if we can visualize what we're doing when we operate our cameras. Once you know that sensor size doesn't change depth of field, just makes it easier to use bigger lenses with larger entrance pupils, or that focal length doesn't change depth of field, also because long lenses just mean larger entrance pupils, our understanding of what's going on becomes a bit clearer. Plus, you won't have that annoying urge to waste time correcting the internet. Thanks for watching.